Wow, we'll take a look.
Come on.
Let's take a look at your ball model with a light.
My
Go
ball
get a light
model?
source. Put some cameras
Yeah.
on it. Let's take a look at what you got, retard.
Alright.
Let's take a look at your globe model, stupid.
My globe model. It
Yeah, your
actually
non-existent thing.
It proves the point.
Your imaginary fucking religion.
The final
globe religion you can't make physical.
My globe religion.
The final experiment.
That's the thing. That's the thing.
Was that a religion too? What are you in a sun cult? Final experiment of what?
Apparently the globe.
What are you in a snowball cult? Let's go make snowballs.
The final experiment.
There was no experiment, you fucking retard.
There's a thing. Yeah, there's a thing called
Looking in the fucking sky is not experimenting on nothing.
I just said the final experiment. What's wrong with that?
Right. So it has been proven before. So if the Earth is truly flat, you can see from if you're from one side of America, you'll be able to see New York if it was flat, but you can't because of the curvature.
That is not an argument. You've never measured curvature, and if you did, please post your measurements. I want to see.
It's just simple. It's simple facts that if the Earth was truly flat, it was like, and we're talking about truly flat, like you're explaining, you would be able to see like the other side of the country.
That is not true. No.
By a microscope.
That is not true.
I think that it's pretty clear that the Earth is neither flat nor a sphere.
No. Okay, so look, the Australian guy. What's your name? Samurai. Hey, bro. I think a lot of people come in here have like misconceptions about what flat earthers think, right? You're probably thinking of some disk in space, right? Like a flat, like all the other planets round, and then we got this like flat disk, and we also think that's ridiculous.
What it means. Yeah.
No flat earthers claim that. We're not even claiming to know the shape of the Earth.
I don't think that's true.
What are you claiming?
No, it is true, right? Every single flat earther in here, right, will tell you the same thing. Right? We don't claim to know the shape of the Earth. Flat isn't a shape.
Yeah.
Right? It's much different to the propaganda you see, right? If you look at on YouTube or something like that.
Is the Earth the size of a donut?
No, bro, we're not claiming to know the shape of the Earth, right? So we're talking about the surface of the Earth, right? So, like, okay, firstly, we all experience a flat stationary. That doesn't prove it is that. That's our basic reality that we all experience, right? Like, you've never seen the curvature of the Earth. I've never seen the curvature of the Earth, right? But they tell us it's a globe, right? They told us that from a young age. Okay, so when we actually go out to a large body of water and we test for the curvature, right? Because you should have like 66 miles of drop over just 10 miles. Right, but when we go out, it tests flat. Yeah, on a globe.
66
right?
miles of drop over.
Sorry, I meant to say foot. I meant to say foot. My bad. Yeah, 66 foot of drop over 10 miles. That's like a 6-story building.
How are you gonna explain then how we got the pictures from outer space on?
Yeah, man, if you look at like the main images that NASA gives us of the Earth from space, if you actually look into how they make those, they take a bunch of low altitude images and then they stitch them together. Right? This is how NASA claims.
There's literally a photo taken from the moon, mate. I don't know where you're going from.
How does the flat Earth explain a 24-hour sun?
Yeah, that's
Hold on. Okay, so which question? Like you asked a question and then I was about to answer it, and then the other guy jumped in and asked a different question. So which question did you guys want to go with?
We'll go with
let's go with my question.
We'll go with that guy's then.
Yeah, okay, so explain how a 24-hour sun in Antarctica debunks a flat Earth.
I didn't say that it debunks a flat Earth. I just said how does flat Earth explained in flat Earth? Or sorry, how is a 24-hour sun?
So it's explained in the globe model, right? But the globe model, it's just a model, right? There's other aspects of the globe model like curvature, which we've completely debunked. Long-distance observations and laser tests. You can have a model, right? Yeah, I'm explaining it to you, dude, right? So flat earthers don't make claims about things they can't validate. right? Like, what is the sun? Where is the sun? How big is the sun? What medium is the sun located in? What's the sun made out of? We don't know those things because we can't validate them. The globe makes a bunch of outlandish claims about things like positive claims, right? Like the sun is a big burning ball of plasma and gas inside a big giant space vacuum. A ball of gas in a vacuum and all this stuff. So what flat earthers are mostly doing is actually putting the globe ideas to the test. Curvature, motion, gas pressure, all of these different things. We don't make direct claims about exactly how the sun works, right? The globe explains it. 24-hour sun in Antarctica. That's just an explanation, right? Explanations aren't proofs. It's just written on a model. There are flat earthers that do have models that explains the 24-hour sun. Various different ways, but I think that those models
skeptics.
Yeah, because we're actually because the globe Earth tells us, right? That globe Earth model says that it has a radius of 3,959 miles. That means that it has to have a specific rate of curvature over distance, right? So if you go to any large body of water, right, like the ocean or a giant lake or something like that. Yeah, it would have to drop over distance, right? You would have to have a horizon at a set distance. Like when I was at school, right, they teach us that if you're standing at the shoreline of the beach, the horizon is roughly 3 miles away. So 6-foot observer height, 3 miles away should be the horizon line if the Earth's a globe. Now we have amazing consumer-grade technology that's affordable, and people are going out and they're seeing 10, 20, 30 times further than you would be able to see on a globe. Right? And then they've gone out with high-powered lasers, right? Some of these have been, teams of field engineers have gone out with like a $30,000 laser, and they're shooting the laser across the surface of the water at 30, 40 miles. Right? They've done all these different tests, and they're hitting the target on the other side of the body of water. Whereas if the Earth was a globe, they should have hundreds of feet of curvature between point A and point B.
All I can say is that I'm skeptical of that.
Yeah, you can be skeptical of it, and you should be, right? But you can actually, the good thing about these tests is you can actually like do them yourself. Right? You can get these high-powered lasers, but you can also just get like a super zoom camera, like a Nikon P900, for like $400 or $500, and you can go do these long-distance observations, right? That's what I did. I lived on Lake Macquarie in Newcastle in Australia. It's like one of the biggest saltwater lakes. And we had an 18-kilometer stretch, right? And I saw all these observations. I'm like, damn, crazy. I'm going to have to go test it for myself because I don't want to just believe these videos I'm watching, right? So yeah, I had a boat, right? And I did like about 7 different tests on different days at different times of the day. And I was just setting the camera up close to the surface of the water, and I could zoom in and I could see the shoreline on the other side of the body of water, right? There should have been a ton of curvature between point A and point B. I shouldn't have been able to see the other side of the lake. So yeah, it's like all of these types of
and
tests,
how did you
right?
control? How did you control for like the variables?
Which variables?
Like refraction.
Yeah. So what do you know about refraction? What do you think refraction is?
Well, what is it? Snell's law, right?
Well, Snell's law.
If you have a change in the density of a medium, then it changes the angle of the light.
Yeah. So you're talking about like atmospheric refraction. So yeah, atmospheric refraction can do many things, right? It can give you like a whole list of different types of effects, right? Like looming or sinking or stooping or superlooming, mirages, that kind of thing. Right? That's why you repeat these tests over and over again, different days, different times. Okay, but refraction doesn't allow you to see magnitudes further than you would be able to see. Right?
Why not?
Because you have to have a geometric horizon if the Earth's a globe. So if you set up the camera at 1 foot off the surface of the water, right, then you should have a geometric horizon if the Earth's a globe at just 1.2 miles away. If you're able to zoom in, see something that's 10 miles away, like the other side of the lake, or an object that's there, like a distance marker, there is no type of refraction that allows you to see that far. Right? It's not what refraction does. No, absolutely not, man. You can look into it.
If it bends light, then it can bend it around a horizon line, no?
No, that's not how it works, right? You would have to say, right, this is what you would have to say is going on. You would have to say, because you can't move the horizon on a globe. Okay, it's a physical horizon. Okay, so what you would have to say is really there is a horizon there at 1.22 miles right, from 1 foot observer height, and everything behind it is just perfectly refracting up and make it look like it's flat, completely flat. Right, so at 5 miles, at 6 miles, at 7 miles, everything's just perfectly refracting up, right, behind this invisible, undetectable horizon. It no longer even matches the definition of a horizon anymore. Right, look, do you want me to show you one of these observations quickly? Show you what I mean.
Oh, I mean, sure, but you don't have to because, like, it can happen.
Oh, right? It can't happen. That's the thing. It's not able to be demonstrated on a smaller scale. Refraction will allow you to see ridiculous amounts past a physical horizon.
Well, that's because a scale. You would have to
like a word. It's like a word. Sorry, say that again. Say that.
That's because over small distances you'd have to have incredibly different, or you'd have to have incredible differences in temperature.
No. The refraction, right? So you can have different types of refraction, and it's just to do with the vertical temperature gradients, point A and point B, right? So if you have like warmer air closer to the surface and then cooler air above it, you can have a refraction effect called sinking refraction, right? And that will make the horizon look closer than it normally would, and then
that'll make it look further.
No, it makes it, dude.
Sinking refraction.
Yeah, sinking refraction will make the horizon appear closer than it should, right? And it will make objects that should... Dude, hold on a sec. Let me finish my sentence, and I can provide citations for what I'm saying. I'm not just saying random stuff. I can back up everything I'm saying with citations. Okay, so sinking refraction is where you have a vertical temperature gradient, and you have warmer air closer to the surface, and then a layer of cooler air above the warmer air. Okay, so what that does, it makes the light refract in a certain way that you get an effect called sinking, right? And sinking refraction, right? I'm going to read out the definition right now, right? So, again. Okay, so it's a refraction effect in which an object normally visible on the geometric horizon, right, apparently sinks beneath it. And then go on to read what I was telling you about the temperature gradients. And then you can have an inversion of that temperature gradient. You can have, like, on a different day or a few hours later, have an inverted temperature gradient, and you get an effect called looming, where things seem higher than they should. But there's no type of atmospheric refraction that allows you to see countless distance past a geometric physical horizon.
Sorry, you broke up for that last sentence. I didn't hear it.
There's no type of refraction that allows you to see these ridiculous distances beyond a physical horizon line. Right, and the problem here is you guys can't actually prove there's such a thing as a geometric horizon. Right, you have to have one on a globe. But when we're going out and doing these observations, we can see the horizon 10 times further than what you would be able to see it on a globe. That's why I wanted to show you a.
In extreme cases, sure.
Yeah, but this is what extreme cases?
These are due to the light curving around the horizon. Due to sinking. Due to sinking refraction.
No, sinking refraction, dude. Look, sinking refraction. It has nothing to do with the globe Earth. It has to do with vertical temperature gradient. To do with the weather. It has nothing. The horizon has nothing to do with the globe.
Connected. The story is beautiful. Of course, they're connected.
Oh, it's not. It's not connected, right? Because you guys can't validate there's such a thing as a geometric horizon. We can invalidate the geometric horizon with these observations, but you guys aren't able to prove it exists. Because what a horizon really is just a line between vanishing points. Right? That's how it's taught in advanced art and architecture mappings. That's why you can't map in a video game. You still have a horizon because it's just a product of perspective. Right? Like video games, like GTA.
I feel like we have different definitions of horizon.
Well, I can read my definitions out and provide citations for them, and I can also show you your definition of a horizon, right, which is geometric horizon, and the observations don't match the definition.
To me,
what's your definition?
To me, a horizon just means to me a horizon just means like the hump due to the curvature of the Earth, past which you can't really see the ground anymore.
Yeah, exactly. Yeah, no, I agree with you. If Earth was a globe, that's what the horizon has to be. Right? And it has to be a certain distance away, depending on the height of the observer. And anything that goes beyond it would start to get hidden by it, behind it. I mean, like to say...
not necessarily. Depending on the height.
Yeah, because even in your definition, right, it's still the line where the ground and the sky meet. Right? It's like the physical leading edge of the sphere Earth, basically. So depending on your height, right, so say you're 6 foot tall, and you're standing at the shoreline, right, this is what they taught me at school, and the horizon has to be 3 miles away. Anything that goes past that 3 mile horizon line will start to be hidden by the horizon.
Bottom up.
Bottom up. Yep, exactly. So once you actually go out and try to test this horizon, you find that doesn't happen. Right? You're not able to see that happen at that 3 mile mark. Instead, we can set the camera up, right, and we can see 10 times, 20 times, sometimes even 30 times further, right, and we can see the horizon behind an object that's 10 times, right. So you'll see. So you should have a horizon at a set distance. So say it's 3 miles. You'll see an oil platform 10 miles away. And then you'll see the horizon behind the oil platform. So on a globe, right, that oil platform has to already be hidden behind the horizon. It's the only way it can happen on a globe, but we see the horizon behind the oil platform.
How would flat Earth explain, like, when you zoom in and you can't see the bottom of the oil platform?
You can zoom in and you can see the bottom of the oil platform touching the water, right? And you can also see the lights on the oil platform reflecting on the surface of the water, and then you can see the horizon behind the oil platform. So it's not obstructed. Okay.
So if I could post a video of somebody zooming in and not being able to see any further, any bigger or any more of the bottom of a ship.
Yeah, absolutely agree with you, Ben. Yeah, because sometimes, right, if you have, like I said, if you have particular weather conditions, you won't be able to zoom in and see more of the ship, right? Because you have sinking refraction taking place. What you can do, though, is you can set up a time lapse. You see that happening, right? So you see a big ship out in the ocean, and it's docked, right? It's anchored. Right? You can look at that ship, say, at one time of the day, right? Because usually sinking refraction happens in the morning, or the late afternoon, and happens on clear days, right? So you could go out and film that ship in the morning, and it might look like it's hidden behind the horizon, right? And then you can do a time lapse. And then a few hours later, once the temperature warms up, right, you can have the temperature gradient invert, and then all of a sudden you can see the whole ship again. Like I can actually have footage of that exact thing happening. Right? It's filming a ship that's not docked, it's anchored out in the ocean like a big giant cruise ship. And you'll see it looks like it's hidden behind the horizon, and a few hours later you can see the whole ship again.
Okay,
it's literally, well, hold on one second, just let me read this one thing out again. Okay, so sinking refraction, a refraction effect in which an object normally visible on the horizon apparently sinks beneath it. Right? It's like textbook definition, sinking refraction, and that doesn't always happen. Right, so if you've got different weather conditions, like we don't have much sinking refraction where I'm from in Australia, right? So if you see ships sail out, they don't do that. They don't disappear bottom up. They just get smaller and smaller and smaller, and then they kind of fade into the opacity of the atmosphere, right? You can't see them anymore. They don't just like have that drastic sinking effect you see sometimes. It's just a different atmospheric effect, right? A different type of refraction. I'm not saying it proves a flat Earth. I'm just saying that when you see that effect happening, I wouldn't be using that as like proof that it's a globe.
I didn't say the reverse either. I didn't say that any refraction proves that the Earth is round, but I think that if you use any type of refraction to say that, to put any doubt on flat or on round Earth, then I think that it's right for me to say that a type of refraction can put doubt on flat Earth. But don't you think that's fair?
I'll say that last sentence again. Sorry.
So like if you use refraction to put some sort of doubt onto round Earth, I think that it's perfectly fair for me to use refraction to put doubt onto flat Earth. Don't you think so?
Oh yeah, absolutely. You're right. If you had flat earthers using these observations to say this proves that the Earth is flat, you could definitely use that argument. But we're not using these observations to prove a flat Earth. We're using this to test.
I'm not talking about like somebody who's saying that the Earth is flat. I'm talking about just to put doubt onto the idea of a flat Earth at all. Just any.
Yeah, I know. I got you. Right, and all we're doing, right, is we've been told that the Earth is a specific size, right, and along with that, right, that comes with a geometric horizon. It has to be there depending on a certain observer height. So what we're trying to do is find it. Right, we're trying to find the drop over distance and the geometric horizon, and then we're looking to the globe side to be able to prove there's such a thing. Prove the Earth curves. Prove there's drop over distance. Right, because we all experience. Well, hold on. Because we all experience the Earth as flat and stationary. Right, that doesn't prove it is, but that's the starting point. Right, and then if people want to tell us no, actually it's a globe and it's spinning. Right, then okay, cool. Then it must have a geometric horizon. It must have drop over distance. So where's the evidence of that? Right, that's where we're coming.
Sure, but I think that given the stuff that you know or that you understand about refraction and different things like that, would you say that it is possible, at least, however minimal, that it is possible that the standard model is correct? Like what most people believe?
Yeah, it can't be, because there's no type of refraction that can allow what these observations and laser tests show us. Yeah, it's okay. So what they're saying,
even if like whatever you think, like if it's perfectly refracted around the horizon, you don't think that's possible. You don't think that it's
so
possible
what you can
for the light to be bent perfectly downwards so that it hits the observer.
No, because these observations debunk that, right? Because we have the horizon behind, right? So when I post the observation in the side chat, it's just, it will help me explain it if you're looking at what I'm talking about.
Okay.
So because we can see the horizon behind the oil platform, it can't be in front of the oil platform. On a globe, the horizon has to be in front of the oil platform.
Well,
there's no type of refraction that can make the horizon behind the oil platforms.
Actually, I think that there is.
Okay, so that's the problem. Like, saying there is, like once
I can tell you
to prove that, you won't be able to.
I can tell you how it could happen.
Okay, go ahead.
So, like, you're familiar with Snell's law, right?
Yep.
if you and you know like what Snell's law is, right? So if you have
it has nothing to do with the refraction you're talking about. It has nothing to do with it.
Oh, hold on, I'm talking with Anti-Globalist.
Yeah, and I'm telling you, that the refraction you're appealing to, in order to save, you're begging the question of the Earth being a sphere in which light can travel around, right, has nothing to do with Snell's law.
I was trying to have a conversation with Anti-Globalist. I could talk to you afterward, but I was about to say
on that, right? He's going to educate you. He can pick up where I've left off. How's that?
I mean, you've just interrupted us, but okay.
It's an open panel. Remember that.
Well, I understand that, but I was trying to have a conversation with you, and I was just interrupted when I was trying to explain myself. Does that make sense?
Yeah, it's irrelevant. It's a red herring because it has nothing to do with Snell's law. Sorry.
So are you going to hear me out, or am I just going to keep getting interrupted?
Okay, what's Snell's law?
So Snell's law is whenever you have two different, like the density of two different media changes the angle of light that passes through it. So like if you have one media,
layer, right?
if you have one media, let's say air, and it passes into a denser media, it doesn't have to be air, it doesn't have to be water, it could be just a denser media. So like just denser air. If it passes from less dense air into denser air, then it'll change the angle that the light is traveling.
Right, so Snell's law doesn't directly apply to one medium, right? So you're still having refraction, right? You're still having atmospheric refraction, but Snell's law is when light moves between two transparent mediums, right? And then you have a boundary, right? Like just say you've got a glass of water and you've got air outside the glass of water, and then you get an object like a pencil and you sit it in the glass of water, right? Then you can use Snell's law because you've got two transparent mediums, right? Because Snell's law requires two transparent mediums. And that's why it doesn't directly apply. Yeah, because we're talking about differentials in density of the air. In one medium. Right, so that's why
the whole range. The air is transparent.
Cool.
Wait, can I respond? So the air is transparent the whole way through.
Yeah, it's only one medium. And
no. Hold on. This is the thing. So
yeah, this is the thing.
You said that. Wait.
Let T-Dub finish, and then you can reply to him.
You're arguing for a curved path of light. So light's traveling in conjunction with the surface of the Earth's curvature, right? That's what you're claiming, that it's curving over the horizon, following the arc of the Earth and reaching your eye, right? Not straight lines. Snell's law's refraction, right, is measured in angles, straight lines, angles.
Okay, so you're partially right, because if you have a gradient of temperatures, then it will result in a curve of light. So like, have you taken calculus? T-Dub?
No, this is irrelevant, right? The light is going to travel.
It is relevant. So you don't know what I'm going to bring up, so why are you saying that it's irrelevant?
As it passes through the surface boundary, right, into the different medium, right, it's going to change angle. It's going to be traveling straight, and it doesn't matter if that boundary layer is curving or flat or whatever. It's going to affect the angle at which the light's passing through it.
Yes. So
correct.
Just imagine for me for a second. Okay. So let's say that we have a cup, right? And the cup is filled with air that's more dense than the air surrounding it. Under Snell's law, this light passing through this cup would also refract. Do you disagree?
I'm not sure. Snell's law is what T-Dub said, right? When you're dealing with just a straight line, and then it will hit a second transparent medium, and then the angle will change.
Yeah, that's what I'm talking about. That's
not what I'm talking. So that's not what that's not what's happening in the
You're gonna have to bear with
one medium.
You're gonna have to bear with me here. Okay, so just my initial question. All right, if you have less dense air surrounding a cup full of denser air, let's say you have helium surrounded by a cup of oxygen, and you have light passing through that cup, will the light refract or not? I mean, it doesn't even have to be helium and oxygen. It just has to be, let's say, hot oxygen outside of the cup and cold oxygen inside the cup. Due to, are you aware of the gas law?
Yeah, we can get into gas laws if you want, but
so that's the gas law. You understand that in the gas law.
You can't give. Okay, the problem is you're not going to be able to give me an example of what you're talking about. It's not going to apply to Snell's law.
I'm just talking about a hypothetical for right now. Can you bear with me for a hypothetical?
Yeah, I'm trying to visualize it in my head.
Okay, so you understand that in the gas law, with a colder thing, like let's say oxygen, a cold oxygen is going to be more dense than hot oxygen. Yeah. Right. So let's say you have cold oxygen in a glass,
like you would have it in water, and then you have hotter oxygen outside of the glass, right? If you have light passing through that glass, just like if you have water, which is denser than air, on the inside of the cup, and oxygen, which is less dense than water on the outside of the cup, in both situations, you're going to have refraction occur. Do you disagree with that?
Yeah, but in one situation, you would apply Snell's law, right? When you've got two transparent mediums, and if you're just using the gases, right, then you've got one medium, and you're going to have a different refractive index for where the cooler gas is, right? It's going to be more dense. It's going to have a higher refractive index. Which is light's going to slow down more when it passes through the cooler air, which is more dense. So that's why we have different types of atmospheric refraction, right? In these observations that we're talking about, right? Because atmospheric refraction has to do with what you're talking about, and it's not to do with Snell's law because there's not two transparent mediums, right? So then we have to start considering what type of atmospheric refraction effects are going to be taking place, like looming or sinking. And
hold on, please. So
I get where you're coming from.
My question was just: is the light going to bend or not?
Depending, yeah, okay. So the light's going
in the situation
it's going to slow down more, right? It's going to make things appear higher or lower depending on the vertical temperature gradient, but that's not Snell's law.
Well, fine. It doesn't matter the name of it. Is it going to bend?
Just drop Snell's law. Yeah.
It's going to bend, right?
Yeah, but depending on the vertical temperature gradient, it can make things appear in different locations.
Okay.
It's not going to allow you to see. It's not going to allow you to see 10 times further past a physical object. You're not going to be able to see over a hill because of refraction.
Well, hold on. So bear with me here. All right. So let's imagine now, instead of just two different media, or not media, instead of just two different temperatures of oxygen, let's say 10. Okay. And as you're going from, you have 10 and they go from colder to hotter air. Okay. And you have the light passing through the cold air first, and it's going to move from that media or that density of air to a little bit hotter temperature of air, right? And that's going to bend the light a little bit, is it not?
Yeah, it is. It's going to, but yeah, you also have to consider the vertical temperature gradients, right? Because that's going to give you the
Yeah, they're divided.
Let me explain. Okay, so that's why. Okay, so say you're doing a laser test, from point A to point B in one particular location over 10 miles. Okay, so you're just setting up the laser close to the surface of the water, and you set up like a archery target, other side of the body of water. Shoot the laser across the body of water, it hits the target. You might say, okay, it's bending due to refraction, and it's getting lucky that it's hitting the target because of the conditions of that particular day. Okay, but then we look at 10 other laser tests in completely different atmospheric conditions, different temperature conditions, right? So this time we're going to do a 20-mile laser test over a frozen lake. Okay, and it hits the target again. And then we do a 30-mile laser test over a frozen lake or a salt lake, and it hits the target again. And then we keep performing different tests in different locations, and it keeps hitting the target, hitting the target, hitting the target. It's a big stretch for you to say every single time, just getting this one particular type of refraction where the laser is perfectly bending around hundreds of feet of obstruction and hitting the target every time. It's
yeah, that would be very hard to explain if I'd ever seen any experiment that shows that.
That's what we have to show you, right? I can show you maybe 20, 30, 40 laser tests, right? And some of these laser tests have been done with a $30,000 laser and by a team of engineers, field engineers. And I think they did 17 different laser tests. And I think they have a 180-page PDF document with all the variables, right? Everything's highly detailed, and there's a whole video to go along with it. Right? We can see everything done start to finish.
Well, that's also, a little bit too much. That's a little bit too much for me right now. Can you show me like? That's all good. Can you show me like anything though? Like, can you show me?
Anti-Globalist, I've got a question for you, real quick. Have you heard of Fresnel diffraction?
I have not.
Okay, so or like the Fresnel spot, or like the Argo spot, any of that?
Oh, no. Can you explain it to me?
Sure. So it's you could probably Wikipedia it pretty easily. Basically, what it is the Fresnel diffraction is basically explaining that light moves in a wave and it's not a straight line, right? And this is a whole like quantum theory thing right now because of this. You know the slit experiment where you send a wave through these two slits and they come out and they interact with each other and blah 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 blah.
Yep.
So that's based off of the Fresnel diffraction thing, right? And so what it basically says is that light can interact with itself because it is a wave. It is traveling a larger distance than what is actually described as the distance it traveled, right? Because it's going up and down and up and down and up and down and up and down the entire time it's going forward, right? So basically what Fresnel diffraction does is, and the Argo spot is, you are able to, and this is just the long and short of it, the application of this science and thing that has been proved over and over again is you can shine a laser at a sufficiently smooth ball right in the middle of it. And this is over a long distance. Shine a laser at a smooth ball, and you have a piece of paper on the other side, a significant distance away as well, and you'll get the shadow of the ball on the paper, right? But in the very middle of that shadow, you'll have an illuminated center pinhole, right, where there should be there's no direct line of sight. Basically, what happens is the light interacts with itself coming off of the surface of the smooth round object, and it curves itself over the curvature of the ball or whatever smooth round object you have, and then it refracts itself directly back into the center on the other side. So that right there could be an explanation for your laser tests. And
I don't think that's the same thing. I don't think that's
still have to pass
analogous to this.
The what?
Yeah, it's still, even in your Fresnel refraction, it still has to pass through two mediums. The boundary between two mediums.
No, it's just air, laser.
Yes, it does.
What
it still has to go through two mediums.
What are the mediums?
All this is a diversion away from the original argument anyway. You're basically conceding that there is no geometric horizon, that the horizon is not representative of a physical distance at which point an object will begin to become obstructed from view. Well, you've lost that. You've tossed that out the window. Now you're just arguing about, we're in a begging the question arena where we've begged the question with you, the Earth is a sphere, and we're debating how light's going to behave within the air surrounding the Earth as a sphere. Prove the Earth is a sphere in the first instance, and then you might have an argument for how light behaves in the air which surrounds your sphere Earth. Because refraction, if refraction is going to work the way that you're claiming it does, right? Light's going to behave differently under different conditions as it's passing through a single medium of air. Okay, you already admitted this isn't an argument for globe Earth. You've already admitted this is just me making apologetics for something I haven't demonstrated to be true in the first instance, right? The globe Earth. It's an ad hoc rescue device. Right, so attack the argument, right? So the argument is, if the Earth is a sphere with a radius of 3,959 miles, then every distance to the horizon measurement can be no more than 1.225 miles times the square root of the observer's height in feet, as pointed out by various academic places like Washington State University, for example, gives us those values. Every online horizon distance calculator uses those values. All right, so there's the argument. We don't see that, right? Therefore, the Earth is not that sphere. Right, now that's the argument. Now, if you want to come in and add a rescue device for your globe, right, you're going to have to verify your globe in the first instance. Otherwise, you don't have a globe to defend by using refraction. Do you understand how it works?
Yeah, I understand that.
I just think it's interesting, right, as something to look into. It's just not analogous to what we're claiming. I was just looking into it. I couldn't find any good examples of what you're talking about, but it's really like if they're shining it at the ball.
Arago spot, ARAGO spot. I mean, it's pretty simple and easy to do. I mean, you can set it up and do it yourself.
Yeah. You're never going to be able to account for any kind of refraction. There is no predictive model of it. It's so unpredictable, right? The experts admit that it's so unpredictable that they just go with a standard formula for it, and it doesn't even involve the bending of light. What it involves is increasing the arc length or the total radius value of the Earth. So giving you, therefore, pretending that the surface the surface of the Earth the Earth's enlarged, right? Allowing you to see more of it, right? Because as if it was a larger ball. If you're seeing a horizon that's well in excess of a geometric horizon based on the current value of the Earth that we're given, then what you'll do is you'll guess how far that horizon is, right? And then you'll say, oh, there must be this much refraction happening, through the air at this time. Therefore, it's like, but the standard value is 7/6r, right? So it's just increasing the radius value of the Earth, because your R stands for radius, right? And that's the standard by which all your field experts will use, right? If they're ever going to apply it, because in most instances, they're going to try and work with distances where they don't have to use any sort of accounting for Earth curvature or refraction, because it gets really fucking difficult. And like I said, and it's unpredictable, and you're going to have to take multiple observations before you cherry pick the one that you think matches your ideology, right? It's just better to just work within a tolerance level where you don't have to worry about refraction, right?
So, yes, but secondly, what I was talking about was diffraction, not refraction. It is a different thing. I'm not taking it into account refraction at all. So you can throw.
Oh, sorry. We moved on to something else now. Sorry, I thought you were still talking about refraction. Sorry, my bad.
I actually wasn't talking about refraction at all. I was talking about diffraction. It's a different thing. A couple questions. Why are lighthouses tall? And I'm new to this whole flat Earth. I just joined today because I thought it was interesting. But like, I'm sure this question has been answered a million times. But like, why are lighthouses tall?
But so that people can see from further away, right?
Yeah. So like, if there's no curve, why would they need to make it tall?
Well, there's still potential obstacles in the way. There could be very high waves in between you and that lighthouse, right? And with diffraction and angular resolution, right, that's going to have some serious problems. Right? It's also like you wanted to claim that there's a density gradient, right? So it's going to extend that light up further and higher, where the light is going to be less attenuated, right? Less absorbed, less refracted by the air. Reflected by the air, etc. It's going to have a greater luminosity at a higher altitude. Yep, definitely.
So like
what a dumb question.
The only one that I heard that made any sort of sense was the waves being tall and they're in the way of you.
Everything he said made perfect sense, right? Because you have a denser atmosphere closer to the surface, and light can only attenuate so far through a denser atmosphere.
I understand.
So obviously, you'd want to have it as high as possible, right? So the light can push further through the capacity of the atmosphere.
Yo, Brad, what's the point of a lighthouse?
Are you asking me?
Yeah.
It's bread, as in like breadstick. But I don't know if anyone else was called Brad. That's why I was wondering. But to let ships know like where rocks are, right? So that way they don't go towards the light. And so that way they navigational beacon, right?
Okay, so obviously you can see the benefit of being able to see the light, like being able to
further
make
away.
light go farther, right?
Yeah.
Okay, so now just imagine in your head a flat plane. You have two towers. One is short and one is long. Which one's going to make one short, one's tall? Which one's going to make the light go farther?
Well, assuming that
it wouldn't matter.
Hold on. Assuming that they are emitting the exact same amount of light, there's no obstacles in the way, and they are on the exact same, they're on the same tower. Let's say there's a light at the bottom, light at the top, emitting the exact same amount of light. There's no obstacles. They should go the same distance.
Okay, so if you're at the base of a tower, and you're looking out to the horizon, and then you go up to the top of the tower, you're going to see the same distance. Is that what you're saying?
No.
Why not?
If it was flat, yes. If it was flat,
yeah. If you're at the top of the tower, you're going to be able to see further.
No, because the way our eyes work, we resolve anything that's above the minimal angular resolution, right? And when you increase your observer angle,
new to this whole argument thing. What the fuck is a minimal
when you increase your observer angle, you're increasing the angular resolution that you could see these things with. At the same distance, you're going to have a higher angular resolution, right? So it always helps, whether it's a globe or a flat.
Are you saying that you're looking at
Hey, dude, apparently, like, according to you, you could put it at 1 foot, and somebody could see it from 10 miles away.
Yeah, that's actually exactly what
that's
dumb.
According to you, you don't even need. You should just go and just tell them they're all wrong. You're stupid. Just put it down at the ground. It's the sea level. Refraction will take care of the rest. People will see it.
No. No. If it were flat,
isn't that what you said?
Okay.
No, if it was flat, yes, but it's not flat. It's round.
No. The argument for being able to see a horizon, right, well in excess of a geometric claim, right, is because light is bending over the curve and allowing you to be able to see things which are much further away.
But not over a variable,
right?
Not over a variable distance.
Yeah. So why are you putting lighthouses higher to see over the curve if you can just put it down and let refraction take care of the rest, right?
Because it's not over a variable distance. It's only over a certain amount of distance.
So
that refraction takes care of anything.
That's not true.
So
I mean, at any specific point in time, the refraction is only going to be able to refract the light a certain amount. It's not going to be able to refract it over a variable distance over a specific amount of time. If you have multiple times, so like if we're talking about like morning on one day to the night of a different day, yeah, there's going to be different distances that the light is refracted, but over a specific point in time, there's only going to be one distance that the light is refracted, so you wouldn't be able to just let refraction take care of everything.
You're basically going to make your globe unfalsifiable, right? Because we could give you examples, right, from sailors' logs, right, where lighthouses have been seen from distances far in excess of the allowance of the globe geometry, right? And you're going to just cry, well, that's refraction, right?
Well, I mean, that wouldn't be unfalsifiable. It would just be very, very difficult for you to falsify.
What would be the point of arguing for asking why they put lighthouses high? Because you think that
I wasn't the one who brought up lighthouses.
Yeah, well, somebody did.
Yeah, it was me. And the diffraction thing still proves that.
No, bro.
I mean, if you want to look at it,
in your head.
Okay, all right. It doesn't prove it, but it has been proved.
Do you know what diffraction is?
Yes, I know what diffraction is. Do you know what diffraction is?
He doesn't know how.
Like a rainbow. That's an example of refraction.
No.
Right.
Yes. So do you know what a rainbow is?
That's an example of diffraction, right?
Yes. And do you know what causes a rainbow?
What is the diffraction helping you out with this globe? Like, what is it doing?
A rainbow is caused when light diffracts around the
We're not talking about this. That was just an example. I'm saying, what is your...
Well,
I'm pretty sure that diffraction helping you. Refraction.
Here, let me explain it.
There's a very good Veritasium video that explains how rainbows work.
Can I stream to y'all? Is that something I can do? I'm not in here often.
Last time I checked, right, the breaking up of light into the visible spectrum, right, into different colors, right, is due to refraction.
I think that's true.
This is true. Do you know what defraction is?
Diffraction, Rayleigh's criterion, I don't understand it fully, the math fully, right? But basically, with distance, light, two separate light sources will appear to converge, and you won't be able to distinguish the difference. They'll just look like one light, right? That's diffraction. Actually, diffraction. Yeah, diffraction is also. Okay, yeah, someone else is going to have to take this one because I'm not. But I do understand that when two lights appear to converge because of distance, that's due to diffraction. Yeah.
Diffraction is like when like the light bends around a curve because it's a wave.
Yes.
Yeah, that would not apply to a globe Earth, right? So what I've been looking up while you guys have been talking, I mean, look, it says diffraction would not allow someone to see further around a globe Earth, right? Diffraction affects like the bending of light around edges, extremely small for visible light due to its due to being short in wavelength, short of nanometers.
That's the thing.
The curvature of a globe Earth would create an obstruction much larger than the scale of light's wavelength, meaning diffraction would not bend light enough to peek around the curve.
So, yes, what they're saying is that you're not able to look directly out from one side of the globe and look all the way around or all the way down. What you are able to do is you're able to look further because the light is coming towards you from across a little bit of the curve, not all the way. Typical diffraction is used to describe going all the way around a circular object. You're not doing that here. You're only doing a little bit.
No, that's not what happens, right? You're talking about a specific example when you're shining a laser beam at a ball.
Yeah, and that
so you don't have okay, so you're not able to at a ball, right, and use something right like a light source, right? You can shine a light source all you want at a ball, right, and you're going to have a shadow behind it. You're not going to have a little bright spot in the center of it, and everything on the backside of the ball is going to be dark, right? You don't have the sun shining its light at the Earth and then having the dark side of the Earth.
Not only that,
because of diffraction, that's not how it works, dude.
Not only that, but it's about like slits. So diffraction only occurs whenever it's a slit in.
It's completely. It's not analogous to this conversation, right? We should be talking about refraction.
Yeah, it's refraction is what causes this phenomenon.
It's not just slits,
and refraction has nothing to do with a globe, right? We need it's just to do with light and the mediums. You can't say
all I'm trying
the globe. You can't enter the radius value into any formulas in relation to refraction.
Well, no,
you can.
The question. But the fact of the matter is that the refraction causes light to bend, and like if the Earth is a globe, then it is possible for that light to bend around the curve.
Yeah, that's diffraction.
That's all we're saying that refraction has to do with the globe, not that like refraction causes a globe or that a globe causes refraction. Just that
refraction
it would explain this phenomenon.
Yeah, but refraction can't allow you to see magnitudes further than you would be able to see over a physical obstruction.
Sure,
there's no small scale examples that show that that's possible, right? You can see it can make things look like they're hidden, right? Even on a little flat surface, right? You can change the temperature gradient, right? And you can have a little toy boat on a flat table. And then you change the temperature gradient, and all of a sudden it'll look like the boat's hidden behind the horizon. But that's just a refraction effect, right? It's called sinking.
Yeah, so why can't that be done the reverse? Why can't the temperature gradient cause something to rise up above a horizon? If it causes something to rise up so that it obstructs an object further than it, why can't it rise up to make an object visible? Make an object visible.
No, because it can only lift something. It can make something appear higher than it should, lower than it should, right? And there's other effects, right? Like superior mirages, inferior mirages, and things like that.
You said that this refraction that you're talking about can only make something look lower than it should be. Lower than it is.
Refraction. No, that's only when you have the warmer air, right? You have a vertical temperature gradient, and you have the warmer air closer to the surface and the cooler air layer above it. Then that's when you get sinking refraction. If you have the opposite of sinking, right? You have a vertical temperature gradient, like invert it, right? So you've got the cooler air closer to the surface, warm air above it, and then you'll have looming, right? And that's where you see those images where it looks like a ship's higher than it should. So it's the opposite of sinking is looming,
which like makes the object appear higher than it should be.
Yeah, exactly. But
okay,
that's why I posted this observation, right?
So why is it impossible for something to not appear to appear over the horizon further than what would be expected if you have looming refraction happening?
Looming refraction, it will just make something appear higher than it should, right? You don't have, okay, so in this observation, you don't have any telltale signs of looming happening, and you also have the horizon clearly visible behind the objects. It's very clear, right? On a globe, you have to have a geometric horizon at 3.5 miles.
So hold on, so the looming refraction isn't just going to bring one object with it. It's going to bring the entire scene with it as well, which includes the vision of a horizon beyond the actual horizon. Does that make any sense?
Yeah, how do you know the actual horizon, which you're talking about the actual horizon as the geometric horizon? How do you know that exists? Because a horizon...
I didn't say that I know it exists.
Right, okay, so it has to exist if the Earth's a globe with a radius...
Yeah, I didn't claim to know. I didn't claim to know the shape of the Earth. I just have an educated guess.
Yeah, okay, but the globe Earth requires a geometric horizon. Like, I don't think that's... People cannot,
Yeah,
if you're defending the globe, then you have to be...
Sure, that's fine. But I didn't claim to know that the Earth has a geometric horizon, or that to know that the Earth is round. I just have an educated guess on, yes, there is a geometric horizon. That's my guess, as well as it's my guess that the Earth is round. That's why I'm having this conversation. If I knew, then I wouldn't be having this conversation because we would be pointless. I would know.
So
we can't find...
Sorry, I've got another question. I'm still very new to the whole flat Earth debate thing. I got a lot of probably basic questions. How do satellites stay in space?
We don't make claims. We don't go on things that require speculation, right? Some things we can't validate. Yeah, so what we would say, right, is you can't have outer space because we have gas pressure, right? And gas pressure requires a container, and then you have a vacuum of space, right? So if you have a high pressure system adjacent to a low pressure system without a physical barrier, high pressure will fill the available space, right?
So like satellites aren't real?
No. We agree there's some technology in the sky. We don't know exactly what's going on up there. We do know NASA has a massive satellite balloon program. NASA's first satellite was a big giant balloon, right? This isn't a secret that they have this balloon program, that we see satellites being launched on balloons, crashing to the Earth, attached to balloons. That these reach very, very high heights, and they can maneuver them, and they can keep them up there for a long period of time. And yeah, the government having some sort of technology that we're not completely sure how it works. Yeah, essentially, I don't know, right? When you look up pictures of satellites in space, you just get a bunch of cartoons, right? And yeah, it comes back down to being able to prove, right? If you want to make a claim that there's satellites in space, right, we need to be able to validate that space exists, right? That it's scientifically possible and it exists.
And the live stream videos from SpaceX going from launch pad all the way up to space. What are those?
Yeah, you see about 20 camera switches, right? Yeah, you don't see a single camera view of it going to space, right? And you don't know exactly what type of lens they're using. But yeah, that's something that you would have to choose whether you want to believe it, right? I mean, if you look into, Elon Musk said he put a Tesla in space, right? If you look into that footage, it looks ridiculously fake. Elon Musk even said, well, we know it's real because it looks so fake. We'd have much better CGI if it was faked, right? Because it looks ridiculous, right? There's a whole bunch of problems with it, glitches in the footage, and it's laughable, right? Just kind of like a lot of the moon landing footage is quite laughable. A lot of the bloopers on the ISS are laughable, being caught using harnesses, green screens, augmented reality, hairspray, list goes on. So, I mean, it's kind of hard to trust people that have been busted lying. Elon Musk is a shady character if you look at his past. But yeah, it comes back down to can't have gas pressure without a container, can't have a vacuum chamber without a container, can't have gas pressure next to a vacuum without a physical barrier separating the entropy from taking place.
I mean, if you have something attracting the gas.
So
gravity?
Right.
Another question. Why would the government, the entire world, be pushing the round Earth? Like, what's the point?
Well, it's been instilled in... Okay, so we don't know exactly why someone would lie. So you would have to ask them that. We could only speculate, give you calculated guesses on why someone would lie. So, I mean, we have evidence of the lie, and that's where we stand on that. But yeah, people could speculate all day long about reasons why they would lie. I mean, it was basically implemented into the mainstream education system by the Jesuits, by the Roman Catholic Church over 500 years ago. Most people would have no idea that it's a lie. Most people that work for the government, even most people that work for NASA, right? These are segmented organizations, compartmentalized. Right, so they have a particular job to do on a need-to-know basis, and then an NDA goes along with that. So, I mean, most people aren't lying. Teachers aren't lying to you; they're just regurgitating information. I mean, it's a mathematical theoretical model that we're all taught from a young age.
So, do you still say that it's impossible for the Earth to be the way that these people that you say are lying? Do you think it's impossible for it to be the way that they say it is?
Oh, I think these people that you're talking about aren't lying.
Well, I'm not talking about the scientists. I'm not talking about whether they're lying or not. I'm asking, do you think it is possible for the Earth to be the way that they say it is?
Yeah, it would have to have curvature and a geometric horizon. You would be able to demonstrate that the Earth moves around the sun via experimentation. You would have to be able to validate that you can have gas pressure without a container. Yeah, but that we have highly educated people that come in here and debate this. What's that?
So it is possible, at least.
You're lucky because he wouldn't have even given you refraction until you'd shown that you can have gas pressure without a container.
Yeah.
I just,
Yeah, I don't know.
I just wanted to make sure that you think that it's at least a possibility, that I'm not just wasting my time.
We're asking for evidence to back the claim of a globe, right? And what we get is assumptions and calculations based off assumptions. We're not getting any empirical evidence or practical demonstration showing that there is Earth curvature, which is a requirement of there being a globe. So
I'm not going to say that there's nothing wrong. I'm not going to say that there's. Hold on. So I'm not going to say that there's nothing wrong with this model of the round Earth. You know, like, of course we as humans are imperfect and we don't know everything, and we're going to get some stuff wrong. We just do the best that we can. We get as close as we possibly can. Do you think that there's any other model that gets hold on, I wasn't finished. Do you think that there's any other model that can get closer than this model?
What? Closer to what?
Closer to reality.
How do you know that it's going to be closer to reality?
By the observation of phenomenon.
That's the reality. So you're wondering if the reality can be much closer to the reality?
No, if the model can be closer to the phenomenon, the observations that we have.
Don't expect the reality, dude.
Sorry, you broke up. What?
You don't have to. You don't need a model. You can just directly reference reality.
The
model is to make predictions. So if you just go off of the phenomena, then you can't make any predictions.
The sun's going to rise tomorrow. That's my prediction.
That's a model.
I model, man. Wrong. That's reality.
It could be. So hold on. That's a model, and it could be wrong.
It's not a model.
Yes, it is.
It's not. It's reality.
It absolutely is a model. What reality is?
Talking about what we actually see happen.
Hold on. What reality is that the sun rose yesterday. Reality is not the sun is going to rise tomorrow. That's a prediction. That's a model based off of a lot of evidence.
Based off reality.
But it is still a model.
Prediction based on my experience of reality. Not something that I don't experience.
So you've experienced your model will be something you don't experience. If I get you right, you're telling me that you've experienced tomorrow in order to tell me now that the sun's going to rise tomorrow.
Yes, I've experienced tomorrow, yes, because today was tomorrow yesterday.
No, I'm talking about the future. I'm not talking about today. You're just playing word games now.
Okay, prove me wrong.
I'm not.
Actually, you're playing word games because you're just trying to drag model into encompassing basically anything that you wanted to. You're the one playing word games. You're the one saying that a model is like, hey, the sky's going to do what it did yesterday in the last, 10,000 days before it because I have a model in my head.
So I'm saying
nobody would say that. Nobody would call that a model, dude.
All I'm saying
you're just doing that because you're trying to put anything that you want, anything that you can into the category of models so that you can.
Are you going to let me speak?
Whatever purpose you need. Well, I mean, no, because you're not even listening to what I have to say. So whatever you're going to respond.
I did listen. To
no, you didn't because you kept talking the whole time I was saying it. Yeah, see, you did it again.
No, I didn't.
No. So you know what I'm going to do? You know what I'm going to do is I'm going to mute you because every time I spoke, you spoke. So there's no possible way you could even know what it is you're supposed to be responding to because you didn't listen to any of it. Because every single time I said any of it, you were speaking. So how about we just put you on mute?
I can tell you what you said.
What?
You said that I'm trying to change the definition of the word model to be able to fit anything that I want into it. And I can tell you why that's not true. Do you want to listen to me?
True? Yeah, I do.
Okay. So I gave you a specific definition of the word model as a way to predict things. Okay. There are certain things which fit that category, and there are other things which definitely do not fit that category. One of those things that does not fit that category is the sun that rose yesterday. Okay. That doesn't need to be predicted. We all saw it happen. Okay. And there are things that do fit into that category. For example, the sun will rise tomorrow. That is a prediction based off of a lot of evidence.
A model.
A lot of prediction.
Model?
Sorry, a lot of evidence.
Off of a model. This is the whole crux of the point. So just answer yes or no.
That's your words. Okay.
No, it's yours. I know that the sun's going to rise tomorrow, but it's not rise. No, but this is it. This is it right here. You're saying that right there is predicted from a model.
That the sun will rise tomorrow? That is predicted from a model?
Garbage. That's some garbage, dude. Nobody's using a model to predict. I mean, come on.
Of course, it's a model. It's a very basic model, but of course,
where's the values for your model going to come from?
What?
Where's the values for your model going to come from?
What values?
You're going to have variables and values and stuff to the model.
Give me an example.
The globe model, right? And you're saying it has predictive capability, right? This model that you're saying has predictive capability. Where's the values going to come from?
Well, the only value that we're talking about now is yes or no, whether or not the sun will rise tomorrow or not. So
Where is the values going to come from?
It's a binary set of values.
And where's the values going to come from? And where are the values going to come from?
I'm answering your question. It's a binary set of values. It's either 1 or 0. The sun either rises tomorrow or it does not. That's the value.
And where is that coming from?
Where is it coming from?
Where's the values coming from? How did you get those values?
Well, the value that the model predicts is 1, that yes, the sun will rise tomorrow. And where that's coming from, is the fact that every other day the sun has risen.
Experience of reality.
Yeah, that's how we make models.
Right. Okay. Now, what are you going to refer back to? Once you got your model, what are you going to refer back to in order to confirm your model's true?
There is no confirming that the model is true.
Okay. What are you going to refer to in order to gauge whether your model is within a certain amount of accuracy? Then how's that?
Past experience.
No. What are you going to refer to say that your model predicted something?
Well, like, if you have the model beforehand, you say the sun's going to rise tomorrow, and then it does.
The thing that happened the first time that you experienced, right?
That's what I said. Past experience. Right. Did you not hear me?
So it's not going to be a past experience, is it? It's going to be another experience of that thing again, repeating.
Which would be like, once that thing has already happened, it would be a past experience. No.
Right, but it's going to happen again and then again, right?
But we don't know that it's. We don't know that it's going to happen.
And your model's able to predict that happening. Right?
That's the whole point. We don't know that it's going to happen again. We just know that it's happened.
We don't know that it's going to happen
every other time.
Sure. All right. That's the problem. I don't know if the sun's going to rise tomorrow. I don't know if I should worry about planting my crop.
I don't. I don't know if the universe will continue to exist.
What's the use of a model then? Your model's useless then.
It's predictive. It's predictive. It tells me 99.999999999 however many days there have been. That many times. It's minus the next day. That's the predictive power of the model. It doesn't give me a yes or no. It doesn't give me a yes or no. It just gives me a really good guess.
Because the values for your model come from the thing that's experienced happening. I mean, it's almost redundant. I mean, it's like you're going, oh, that happened. I wonder what's going to happen again, like next time. And then you do your model, and it happens again, and it was the same thing that you first experienced, right? And you're going, oh, my model's correct. It's predictive, right? It's ridiculous.
How is that ridiculous? Because I can make a model that explains a perception in a point of time. Like I could do that, and then the next time the model's proven wrong, and then we stop using that model. Whereas basically, I can make a model. I can make a model that predicts something right, and then that model's useful because it predicts things.
That's the trick of it, right? That's like. The trick is, like, so we see things happening in cyclical nature, right? And then we measure values to it, and then we conceptualize it into some sort of other form, right? Where it involves things happening from a perspective that we don't have, right? And then you say, because you saw these things happening over and over again, and you got the values and all the values from them, that you pretend that your model predicted it would happen again, right? And predicted something, and it didn't. It's just a record of what has already happened a zillion times.
Well, I mean, when we're talking about the sun rising, it's a pretty basic model. I'll give you that. But there's plenty of more complex models which predict things that you or I, like on our own, could not hope to predict.
Right. So I've got a value. I've got 8. Right. What's the problem that gets that solution?
That's very vague.
There's a correct one. That's right. There's a correct one. I want you to tell me what it is. I want you to tell me what it is. Use a model. Use your model. You've got the information. You've got 8. Now use a model and give me the correct one. Give me the one that's the most accurate.
But there's multiple correct ones.
Right. So there's multiple possibilities that where 8 would be the outcome. Right.
Yeah, it's not enough information for me to be able to predict
which one's the most accurate.
Well, I mean, I never claim to know anything. The models don't. Models don't claim to know anything.
Here's a prediction.
I think I don't have enough information to be able to predict which, like, whether you're going to say 4 + 4 or whether you're going to say 3 + 5. Or I don't have enough information.
So beyond the direct experience of what we observe, right, and the values that we can get from that, right. Where does the extra part come in that allows you to be able to say that this globe model here is very accurate?
Where's the extra part that comes in?
That turns the Earth into a globe. Yeah, where's that come from?
So the globe model, all it does is make predictions. Okay, it makes very good predictions.
About what?
It doesn't make perfect predictions.
About what?
Like plenty of things.
Like what?
Well,
Fuck, huh?
Well,
No prediction whatsoever. It's a perfect.
Are you gonna let me? Are you gonna let? I didn't say it makes perfect predictions. In fact, I said
Yes, you did. You just said that right now.
I never said that it makes perfect predictions. I said that it makes predictions, and I said it makes pretty good predictions. And I specifically said that it. And I specifically said
that model
that it can make wrong predictions.
Just like that model in text chat. Let's take a look at it.
Like what, dude? I've been asking you, and you haven't provided what? Like what?
Like what predictions can it make?
Yeah.
I mean, I've heard before, like I would say lunar and solar eclipses, but I've heard before that.
All right. Yeah, but how do you know that? How do you know that it makes those predictions?
I never said that I know. This is what we've been talking about this whole time. That I don't.
You don't know. So let me get this straight. Let me get this straight. You're making a claim that it makes predictions. Now I asked you what predictions. You said I don't know.